Hello everybody, welcome to the ME296 lecture on control systems. We're going to go over some control system basics, a couple of different kinds of control systems, and then a little bit of analysis. What is a control system? A control system manages, directs, commands, or regulates the behavior of other devices using control loops. So control systems can be very simple or extremely complex. An example of a very simple one would be just a regular timer that regulates garden sprinklers. You set it for 5 minutes, you walk away, and 5 minutes later it turns off the garden sprinklers. It's very simple. But more complicated systems utilize the state of whatever it is we're trying to regulate. And they do this by taking measurements of state variables, where a state variable measures a property of the system that can be changed independently. And this is something like temperature or position, which would determine the state of our system. Is it hot or is it cold? Is it to the right or to the left? These are examples of states. Often control systems are integrated into whatever it is being regulated, which requires us to develop control systems notation that is compatible with the other systems we've used. And in our case, for this class, we've used circuits, and then we analyze those using Laplace notation and transfer functions. And we're going to go into that soon. But before we move on, just know that control systems is its very own branch of engineering, and it can get very complicated very quickly. But even the most complex system can be described using the tools that we develop here. So even these basics are very important to learn. And with that, let's jump into characterizing control systems. There are broadly two kinds of control systems, and the first is the open loop controller. The open loop controller does not use measurements of state variables to regulate the system, and this would be the sprinkler timer. You set it for 5 minutes. After 5 minutes, the sprinklers turn off, regardless of if the grass needs more water or doesn't need more water. These are very simple to implement, but these are not suitable for complex systems. Closed loop control systems, on the other hand, do utilize measurements of state variables to regulate the system. Often these are trying to keep our device at a set value or a set point, and this could be an ideal temperature or keeping a robot arm at exactly the same spot no matter what's happening to it, things like that. This does require some kind of measurement, which means some kind of measurement device is required, and this makes these kinds of control systems a little bit more complicated, but it's often much better just to take the time to implement these instead of just kind of hoping for the best with an open loop control system. So most of the rest of this lecture is going to be talking about closed loop control systems and how to implement them in some basic kinds. So there are two kinds of closed loop controllers we're going to go over in this class: bang bang and proportional. And we're going to start with bang bang controllers. Bang bang controllers, also known as on-off or hysteresis controllers, have two states. They're on or they're off, and there is no in between. In math form, this looks like a step function. Everyone should know what that looks like. So let's just look at an example of a bang bang controller in action via a simple water heater. The system we're going to regulate consists of the water tank and a heating element. In our case, we're going to assume it's just a flame, and a flame is either fire or not fire, which gives us two states: fire, not fire, 1, 2. Hence, a bang bang controller is necessary here. Our controller system is going to consist of a thermometer to measure the temperature of the water, and a logic controller to determine if the temperature is right or not, as well as to turn the fire on or off. Ideally, we'd like to keep the water at the exact temperature we set it to, but practically this is impossible, so we're going to have to accept a range of temperatures that we would like to have our water at. This here is a cartoon of our system. We have the water tank on top of the heating element. A thermometer measures the temperature and sends the information to the logic controller, and the logic controller tells the fire to be on or off based on what the thermometer tells it. So let's see how our water temperature behaves with the system going. We're going to plot the temperature as a function of time. I've set the orange line on top as the set point, or the temperature that we would ideally like the water to be at all times. And then the blue line on the bottom is where we've decided that the water is too cold here and then needs to get heated up. So if we start at the ideal temperature, it will get colder since we've decided that flame doesn't need to be on here when we're at our set point. And eventually it's going to cool enough to go beneath the low temperature bound, and the heater is going to need to turn on. It does so, and the water heats up until it reaches the right temperature at our set point, and the fire turns back off. And then the cycle repeats until we turn the water heater off, or we run out of space to plot time on. To illustrate the bang bang nature of our controller, I put on the plot the sections where the heater is on or the heater is off. You can see that when the temperature is within our acceptable bounds, the flame is off, and then as soon as our temperature goes outside of our bounds, the heater turns on. And we can imagine that this is a perfectly fine setup for systems where the set point is not critical, like a home water heater. If your water coming out of your faucet is within a couple of degrees, it's fine. No one's really going to notice a couple of degrees difference. But for more complicated or critical systems, there are some questions we need to ask ourselves, especially when it comes to bang bang control loops. The first is, how long does it take to obtain the measurement? If it takes 10 minutes to get a good temperature reading, and then by the time we realize we need to turn the flame on, the water has continued to cool well below our too cold mark. And how effective is our method of regulation? If we only have a small lighter to heat the water, it's going to need to be on significantly longer than if we had a huge bonfire surrounding our water tank. And the third question is, how much leeway do we have? For a home water heater, a difference of 10 degrees is barely noticeable. But for, say, like a hospital application or maybe an aquarium with some kind of rare fish, we might need to keep the water within a couple of degrees for safety reasons. And these are important questions for all control systems, but especially for bang bang systems, because we can't change our state beyond on or off. And now we're going to move on to proportional control systems. Proportional control systems adjust how much regulatory pressure to apply based on the state of our system. And this means that we have a range of values. Instead of our fire just being fire or not fire, we have a stovetop with an adjustable flame, that kind of thing. And there are three very common types of proportional control, but we're going to clear up some math notation first. The first is the error function of our system, E of t. And this is the set point minus the value of what we're measuring at time t, given by p minus v of t. And then the correction applied by our system has two parts. The first is the gain, which is often denoted by k, which is just a simple multiple. And then the second part is some function of the error. And this function is going to vary depending on what kind of proportional system we're looking at. What kinds are there? Well, the first one is a direct proportional control. And this is just a simple linear relationship between the size of our error function and the correction applied. The mathematical form is just gain times error. So if we had a large gain, we multiply it by whatever error we have to get our correction value. A large gain times, say, an error of 1 would give us a really high amount of correction, a really large flame. A small gain will moderate the flame lower. It's pretty easy concept to grasp. It's just the slope of our correction we apply. The second type of proportional control is derivative action. And the correction applied here is related to the derivative of the error over time. So how fast our system is changing away from our set point. The third type is integral action. And this one, the amount of correction that we apply is proportional to the integral of the error over time. In this case, I've given the formula so that it's since we turned our system on, time 0 to time t, whatever time it is now. But often in practice, there is some time delay that matters, 10 minutes, 5 minutes, however much is important for the system. But for this class, we're going to use our initial time as 0 and not t minus 5 minutes or whatever. Now, all three of these are often combined together into what's called a PID controller, or a proportional integral derivative controller. And in this one, our correction is proportional to all three types of action. Now, why do we do this? Because each of these three types, proportional, derivative, or integral, have their own drawbacks. But if you combine them together, the strengths of one type can override the weaknesses of the other. Now, the mathematical form given should look very familiar to everyone. If we kind of squint our eyes and replace the gain with impedance and the error function with current, this is basically the same equation as the circuit RLC differential equation. So I'm not going to go into any kind of detail about the behavior of this since it's the same as discussed previously. But we can remember, if we remember from our previous lectures and problems, that systems that mathematically look like this exhibit oscillatory behavior and can be critically damped, underdamped, or overdamped. And depending on what kind of system we're regulating with this, these properties are very important to control our state of our system effectively. Now I'm going to go through each of these different types in a little more detail to try and get a little more intuitive understanding. For proportional control, the correction applied in blue is dependent on the size of the error, which is the yellow, between the set point and the measurement, where the measurement is green and the set point is the orange line. So we can see that our correction, our blue line, decreases as our measurement approaches the set point. Now, proportional control like this only takes into account the current state of the system. And this kind of control may result in staying just a little bit away from the set point for long periods, since the correction is going to be small when the measurement is close to the set point, and maybe whatever's trying to keep our system away from the set point is going to be able to overpower our proportional controller when we're relatively close to our set point. Now, for derivative control, the correction is proportional to the slope of the error. We see here that we approach the set point in a straight line, and we have a constant value correction. If this was a curved line, we'd have a curved correction value applied. But I think it should be immediately obvious the drawback of a derivative action. And that's, what if the state of our system is not changing? What if we're steady state away from our set point? What's the slope of a straight horizontal line? It's zero. We'd have no correction applied because no matter how large our gain, our error function gives us zero, so a high number times zero is just zero again, so we're not going to get any kind of correction. So when you have something like that, it's useful to take into account our system history, just like the integral controllers do. We see that in our model system, the error is constant, like it would be if we had a steady state error like we just discussed. Now, integrating this throughout the time gives us a constant increasing correction, because you have a straight horizontal line. The integral of a straight non-zero line is going to be just a simple slope proportional to the magnitude of our straight line. So if our system's being affected by an outside force, like say whatever force is keeping our system a set value away from our ideal point, an integral action controller is going to apply increasing amounts of correction until we're able to overcome this outside force keeping our system outside of where we want it to be. So you can see that when we combine all three kinds, we can overcome different kinds of forces, keeping our system away from our set point value or our ideal value. And now we're going to talk about a little how to integrate this into circuits. We need to get these into the Laplace domain so that we can integrate them with our transfer functions of our circuits. So luckily for us, we've already seen how to get mathematical equations into the Laplace domain. So I'm just going to show the results here. And then from these, we can create a transfer function of the control system, which we can now combine with the transfer function of circuits. But before we do this, there are a couple of new diagram symbols to go over to make analyzing things a little more simple. The first is the summing point. Whatever data or values reach this point are added together or subtracted. And in this class, I'm always going to indicate this with a sign that's next to the line, either a little plus sign or a little minus sign to indicate if you need to add or subtract from the whole. We already know about the box which holds the transfer function, but it's here for completeness. The split point represents where data is being split but not lost or transformed. And this is pretty similar to voltage in that it retains its value no matter which branch it goes down. And then lastly, we need to indicate the direction of our flow, which we're going to do with just arrows. And now we're ready for some new algebra. Here is a model system with some kind of input X and some kind of output Y. And there are 3 circuits or controllers. And how can we determine our output? We need to simplify this diagram, just like how we would if we were looking at transfer functions of multiple circuits being added or put together. So we're first, just make sure we go through everything. X is the input. A is our value after our summing point, because we need to change it so it's no longer just our input X, it's X plus or minus something else, so we're going to call that A. On top we have 2 transfer functions, G and H, and in between G and H we have a whole new set of data called B, because we have A modified by whatever happens to it through G. Then we have our output on the other side of H, Y, where that value of Y is then fed back into our third transfer function, J, which then goes back to our summing point and is subtracted from. So the very first step is just to take the output of the summing point. It shows that the input X is added and the return of J is subtracted. And the return of J we find by looking, and we see that the output splits off and leads to J. So the return back to the summing point from that J branch has to be Y times J. The next thing to do is to combine the transfer functions that we can, simplify them. And in this case, G and H are in series with each other, and we know that this means we simply multiply the 2 together, and we're going to call that new transfer function L. Once we have L, the output Y is equal to A times L. We're almost there. To get our final relationship between X and Y, we need to substitute our equation of A into our output Y. So now we have our output Y is equal to the quantity input X minus Yj quantity times L. And then after a little bit of rearrangement, we can get the output all by itself, which tells us that our output is proportional to input L over 1 plus L times J. Since the output comes back to the input and then is subtracted, this is an example of negative feedback. Our output is fed back to our input and subtracted. Even though we fed it through J, which modifies it in some way, that's still an example of negative feedback, because this modification might simply be our control system gain. So we don't want it to subtract everything away, just some value of it, or maybe more. Depends on the function of our system. So this right here, on the bottom of the screen, our output divided by input, which gives us just the transfer function as it's a ratio of out over n, equal to L over 1 plus J times L. That's the general form of all negative feedback functions, where L is our system that we're trying to regulate and J is our control system. Positive feedback is very similar to this, but I'm not going to go through that now because you're doing it in your homework. And then we're soon going to go over some implementations of control systems, especially with our lab that's coming up, or depending on when you're watching this, has already happened, a temperature controller. But that's all for now.